Welcome to qnawire.
For problem 130, we are asked to prove that the centroid of a pyramid is at 1/4 of its height, no matter how many sides it has. And to find the centroid, we'll use this equation where the centroid times the volume is equal to the integral of the centroid of the differential element. And that differential element will be a slice along the pyramid, a horizontal slice. So let's say we have this pyramid. We'd be looking at a slice through it like this. Where we have each side of the base of the pyramid I'll call B. We also have the height. And one thing that'll be, and to make a formula that's common to every side, because we have to prove this for every side of a pyramid, we can look at the base of a pyramid. And just looking at the base, if we have one side of the pyramid coming out from the center of the base, well, then we have that half of the base would just be b over 2. And this angle here is going to be pi divided by the number of sides, which makes a length of this triangle b over 2 divided by tangent of pi over the number of sides. So then we can find the area of the base of a pyramid is going to be equal to the number of sides times 1/2 times b times a b over 2 over the tangent of pi over n. And simplifying that, we get that the area of the base is equal to the number of sides over 4 times tangent of pi over the number of sides times b squared. And to make this simpler, I'll just call that constant k, dependent on the number of sides, times b squared. And we need the area of the base times a triangle to find the area of the slice, because we need the volume in our centroid equation, which is equal to the integral dv, where dv is equal to the area of the slice times the change in y. And the y-axis is going straight through. Straight up and down, that is. And so we can relate the area of the base of the pyramid to the slice anywhere in the pyramid using similar triangles. Because I'll call the side of the pyramid along the slice S. And we have a distance y that goes to the slice, and then the slice itself will have a thickness of dy. And so using similar triangles, we know that S over B is equal to H minus Y over H. Therefore, the side of the slice, S, is equal to B over H times H minus Y. So now we can find the differential volume we need, which is equal to the area of the slice dy. So the area of slice will be ks squared, similar to how the area of the base was kb squared dy. And now that we know S in terms of B and H and Y, we can plug in for S. Now we can solve for the volume. Taking the integral of dv we just found from 0 to the height of the pyramid. We get that the volume is equal to kb squared over h squared times negative 1/3 h minus y cubed from 0 to h. And plugging in 0 and h, we get that the volume is equal to 1/3 kb squared times h. Now we need to find the right side of our centroid equation, which is the integral of this differential element centroid, integrating from 0 to the height of the pyramid. Our differential element will be y, because we're integrating the centroid will always be a distance y from the base of the pyramid all the way to the top. Then we can plug in dv that we found as well. And so simplifying this equation so that we can solve the integral, we get that is equal to kb squared over h, pulling the constants out, times the integral of 0 to h of h squared y minus 2hy squared plus y cubed dy. And then solving the integral, we get kb squared h over h squared times 1/2 h squared y squared minus 2/3 h y cubed plus y to the 4th over 4, all from 0 to h. And plugging that in, we get that the integral of the centroid of the differential element is equal to 1/12 k b squared h squared. Now we know everything we need to plug into our original centroid equation that looks like this. So we can plug in the volume we found earlier. Of 1/3 kb squared times h. Instead equal to the integral of the centroid of the differential element that we found. And we get that the centroid is equal to 1/4 times the height, proving that the centroid